Okay, guys. So as I was saying before, this is the last part, this is the last lecture of the course, and this lecture will be split into two parts. The first one will again focus on the behavior of reinforced concrete structures acting under combined bending moment and axial force. Okay? So, as you have seen, as I have shown you during the last lecture, let's see if I can do this. Okay. The class of the material depends basically on the strength of the material. Okay. So for reinforced concrete, we have different classes of material, different resistance strength classes, which are indicated by two numbers, basically, for example, 28 and 35, and a capital letter C. C stands for concrete, because it's a property of the material, concrete, and the two numbers are respectively the cylindrical and the cubic strength under compression. So it means that these values are the values at which that indicate the strength in megapascal that the material can typically bear. Okay, but these are not mean values; they are not average values because the material is not homogeneous. It's material. If we take out of a piece of the material 10 samples, they will not all fail at the same strength of excitation. But we will see that there is a sort of distribution of these materials, of this material property. So some samples will fail at lower stresses, and some samples will fail at higher stress level. This value indicates the characteristic value of strength. This means that out of 100 samples, 95 samples will have a strength that is higher than this level, but 5 of them will have a strength which is less than this value. So this is a statistical property. Now, what changes? What is it? We have here plotted the nonlinear, the inelastic, constitutive law of concrete. I have already said during last lecture that reinforced concrete is not a unique material, but is a combination of two materials. Basically, we have concrete and we have the reinforcement bars in steel. Here we have our nonlinear behavior of concrete. Well, if you remember well, during the last lecture, when I have talked about the behavior of reinforced concrete under pure bending and under pure compression and under combined compression and bending moment, our computation was purely linear. Okay, this was a linear elastic behavior. But in this case, we can see that if we move beyond the elastic part of the material, its behavior is quite complex. We have the so-called parabolic rectangular behavior. In Italian, we usually say that it is la parabola rectangulo that indicates this sort of behavior. An initial parabolic behavior, and then we have that stress, once we exceed a certain level of strain, the resistant stress is constant, doesn't increase any longer, So it seems like a plastic behavior, and the design compression strength is FCD. C stands still for concrete, and D stands for design, because it is the value that we use for designing our structure, per progettare. Well, why am I showing you this? Because the new codes, new national codes, both the Italian code, both the European code, and also in other countries in the world, basically refer to the nonlinear behavior, recommend a nonlinear analysis of the structures. But the resolution of nonlinear analysis is quite complex. It's actually very complex. So, and it involves a lot of computational, straightforward but tedious mathematical passages. So, I don't want to go into details because this would deserve several lectures. But it is important that you know how the reinforced concrete behaves, and the behavior is basically the one that you have seen the last lecture. But it is important that you get also some knowledge about the nonlinear computation of reinforced concrete structures. So even if I will not go into the mathematical details. So just one question for the audience, even in the room or at home. During the last lecture, we saw that in order to deal with reinforced concrete structures, we made 3 assumptions. Any one of you recalls those assumptions? Any of them? This is a typical question for the oral, but I mean, this is not an exam, so.
Is one of them that it rotates remaining plane?
Sorry, can you repeat?
Was one of them that it rotates remaining plane?
Yeah, this is the Bernoulli-Navier, this is the first hypothesis, very good. It means, for the audience at home that could not hear, the Navier hypothesis says that all the faces rotates remaining plane, and this allows us to impose a straight strain domain, a straight strain path for each cross section. So this was the first assumption. Then we had other 2 assumptions. Even people at home, please don't be shy. I'm checking also the chat. Okay, right. Well, the third one, I will spoil the last one, is the constitutive law. Okay, all the materials, both the steel and both the concrete, exhibit a linear behavior, so that the strain is proportional to the stress, and vice versa. Obviously, for these holds for the steel, both under compression and both under tension, but the concrete only reacts in compression. Okay, so let's say the second hypothesis is that we assume the constitutive law of the materials, which is elastic linear. And the last one is a word that I have used like I would say 20 times last lecture. Remember that reinforced concrete is not a material. It composes of 2 materials. So how can we deal with two different materials?
Perfect adherence.
Yep. Good. The perfect adherence between the two materials. So meaning that at each fiber of the cross section, the strain of the concrete is equal to the strain in the steel, the corresponding fiber of steel. So this combined with the previous assumptions tell us that that the steel and the concrete are undergoing different levels of stress. Okay, because the strain will be the same, but since steel is much stiffer than concrete, the stress level of the steel is much higher than the stress level of the concrete. And the homogenization is done by means of the coefficient n, that is usually assumed equal to 15. Okay. Now let's see what changes now. Now we're talking about nonlinear behavior of reinforced concrete structures, but Bernoulli-Navier still holds. Okay, so we will still consider that each cross section will rotate the remaining plane. There is no longitudinal deformation that is nonlinear in the concrete. There is no warping. Then there is perfect adherence between steel and concrete. This still holds, but it changes only the last hypothesis. The material constitutive laws now changes, and so we have the so-called rectangular parabolic behavior for the reinforced for the concrete only in compression always, and we have the perfect elastic and perfect plastic behavior for steel, which works both in compression and both in tension, in tensile stresses. Okay, so this is the only thing that changes. But as you can see, leaving out the perfectly elastic assumption will reflect into a much more complex problem to solve. And this is true for basically for reinforced concrete in particular. Now let's consider a generic cross section. Here we have a rectangular cross section with that is simply supported, so we have only reinforcement at the bottom. This is typically done in order to absorb the tensile stresses that are induced by a positive bending moment. Okay, the bending moment that you usually have in the span of the beam, so that we have tensile stresses and tensile strain at the bottom side of the cross section, and we have compression at the top side. Here we have the compressed section of the cross section of the concrete that is marked with these diagonal lines that ranges between the upper fibers of the cross section until the neutral axis. Neutral axis, in Italian l'asse neutro, means that the strain and the stresses in this point, in all the points that belong to this line, are equal to 0. Okay? In fact, we can draw the shape of the strains, and according to the Bernoulli-Navier assumption, the rotation is linear, so there is no longitudinal deformation that is non-linear in the section, so the strain shape is perfectly linear, and it ranges between 3.5 per thousand, which is the ultimate compression strain for the concrete, and then is equal to 0 at in correspondence of the neutral axis. This is a generic shape. Now, what changes from what changes now when we deal with non-linear behavior of the concrete? During the last lecture, I would have told, okay, well, we know that the strain is linear. So if the constitutive law of the concrete and of the steel are linear, it means that stress is proportional to strain. So if strain is linear, stress will be linear as well. So we expect a linear behavior for the stress profile. In this case, this property does not hold anymore. But at any level of depth of the fibers, we will have fibers which are characterized by increasing levels of strain. Using this diagram, the constitutive law that is here plotted, we can enter in this diagram. We know the level of strain of that fiber, and we obtain the corresponding stress of that fiber. So when the strain is between 0 and 2 per thousand, we are in this range. Here we have 0, here we have 2 per thousand, which is roughly the value of epsilon C2. It means that in this region, the strain will not be linear, will not be the stress, sorry, will not be a line, but will be some parabola. Okay? We'll have a parabolic behavior. When the strain exceeds 2 per thousand, or basically exceeds epsilon C2, the stress does not increase anymore. Okay, so it is constant. So it doesn't mean, we don't care if the strain is 2 per thousand, 2.1 per thousand, 3 per thousand, 3.5 per thousand. The stress will always be FCD. So that's what we can see here. This is the diagram of the strain, of the stress, sorry, that is associated with this strain path. And so we have the parabolic behavior and the longitudinal behavior. We can see that here we have a distribution of stresses, but basically we care about the resultant force when we deal with nonlinear behavior. So we want to know the resultant force that is associated with this distribution of stresses, and it is called Cu, and it is equal to 0.41416 times Windows here. Okay, times the depth of the neutral axis, that has to be multiplied also for the depth of the base of the rectangular and of the cross section, and the stress, the ultimate stress, which is equal to FCD. Okay, this will provide us with the force. And then we have on the other side just the contribution of the steel, because as we have said during the last part, during the last lecture, concrete does not resist to stress, to tensile stresses. That's the reason why we put reinforcement bars, which will provide this ultimate force in tension. And if the steel is yielding, so we are already beyond the yielding strain of the steel, the stress will always be equal to Fyd. Okay? Otherwise, it will be proportional to the stress, to the strain. So the resultant force associated with the reinforcement bars will be simply equal to the yielding stress of the steel times the area of the reinforcement. This is true if the steel is yielded. Okay, but as I said before, as I said before, we have, no, it is better to stick here. So basically, we have this new model in order to tell us how the reinforced concrete behaves, and basically varying only the neutral axis will change the resultant compression force and the resultant tension force. Okay, so according to this couple of forces, we have the possibility to balance different levels of compression forces acting on the structure on this at each cross section, and of the bending moment. Okay, the bending moment will be simply the product of each of these forces, if they are equal, times the effective length. Otherwise, if they are not equal, there will be some resultant force. But what I showed you before is just tell us that given the neutral axis, the structure can resist, can bear a level of stresses which is associated to an axial force and a resisting bending moment. So we have a resisting axial force and a resisting bending moment that only depends on the depth of axial force. Once the structure is designed, so I have already decided what is the height of the structure, the beam, which is the base of the beam, and how much reinforcement I am putting into the cross section. But varying the value of the neutral axis, we can see that we have different scenarios. We can have all the compression purely compressed, all the section that is under compression, and so that will be associated to the pure compression behavior of the cross section. Now, what is the optimal behavior of the structure? Here we have y. In this case, y indicates the depth of the neutral axis from the top fiber, equal to 0.259 times the height, so 1/4 basically of the height. But what does it mean? Basically, what I want to get is that the steel, the reinforcement steel, is yielding, okay, so that we can exploit all the area times the maximum level of stress for the steel. So that's what I want. I want stress to be yielding. And then I also want that this area is as big as possible. Okay? Because it means that I can exploit the maximum part of the cross section of the concrete, which exceeds epsilon c3, so that we can have the highest possible resultant for compression. And the combination of this compression force and the tension will provide me with a good behavior when the structure is under bending. Now, the problem is that computing the integral of this parabola rectangular behavior is very complex, and you can see it. This is complex when the structure, when the cross section is rectangular. You can imagine how complex it is when we have some beam that is not rectangular. So basically, what the engineers do and what the codes allow us to do is to turn this behavior model into a simpler one, which is providing basically the same results. So we are moving to the stress block. This stress block is such that it considers only all the concrete working at the ultimate design stress level, so FCD, but it is not reacting for its entire area, but only for 80% of it. Okay? So we will consider as resisting only the 80%, 0.8 times y, of the distance of the neutral axis. It means that the resultant force will be applied in 0.4 times the height of the neutral axis from the top fibers. This holds both for a rectangular section, both for a generic one, that is indicated here. Obviously, when we're dealing with this different cross-section, there may be some differences in the computation of the resultant, but we can just take into account as it is working with this 80% of the neutral axis times its maximum level of stress. Obviously, we will need to find the different values of the B for this cross-section. That can be non-trivial at all, but we are already exceeding some unknowns. So what is basically done, and this I think is the last slide for this topic, yeah, is this. As I said before, the varying the depth of the neutral axis, the associated resisting axial force and the associated resisting bending moment vary, increase or decrease according to the depth of the neutral axis. So we can consider this as the undeformed line of the beam. Okay, and if in the upper fibers and at level of the steel, we can plot the possible strains that we can meet in our computation. If we consider different scenarios, so for example, all the structure is under tensile strain, what is working is just the steel, which will provide some tensile force. If on the other side we have all the cross-section working under pure compression, we will have these different levels, so that both all the entire cross-section, not only the upper part, but the entire one, and also the steel, will provide some strain, some stress, and so some forces to the resisting neutral axis, for the resisting axial force. All the intermediate situation where the cross-section is rotating somehow are associated to some particular levels of axial force and to a particular value of bending moment. If we consider all these situations and we plot them into a NM diagram, so we have axial force and the bending moment, on the upper part we have compression, whereas down here we have tensile forces. So we can see that the resisting axial force in compression is associated to the scenario E. That is much higher, that is associated to a value of axial force that is much higher than scenario F, which is the pure tensile force, with no bending moment associated. All the other situations will, all the intermediate scenarios will define this domain. It means that the structure, the cross-section, is capable to produce some resisting axial force and some resisting bending moment for all these lines, for these two lines. Obviously, if our couple of axial force and bending moment, the exciting one, let's say, the ones that we find solving the structure, are inside this domain, it means that the structure, the cross-section that we have designed, is perfectly capable to counteract, to resist them, and the cross-section is safe. Otherwise, if we find some values of axial force and bending moment which fall outside this domain, it means basically that the cross-section does not have the dimensions such to resist those actions. Okay, any questions about this? It can seem counterintuitive to perform all these computations and all these analysis just to find a domain, when we just have to perform some analysis, some checks. But remember that when you design a structure, we'll have several cross-sections of several elements. So if you define, if you try to design them in such a way that they are all basically the same in groups, for example, with the same reinforcement bars, you will find that you end up with just one domain that tell you how a lot of elements are behaving. And so you just plot all the couples axial force bending moment into this plane, and if there is some dots falling outside, we have that we have to increase the dimensions or the elements, or otherwise of the reinforcement bars. Something else I was not mentioning is that it is important, it is crucial for safety purposes to have a ductile failure. What am I saying? If we find us here, if we look at it, we can see only the Italians at home can appreciate it for now. We have some part of rotture fragili, so brittle failures, and another part of rotture duttili, in English ductile failures. It means that when we have failure of the cross-section, this failure is associated with a ductile behavior of the structure. Means that the steel is undergoing high deformation. Okay? If we go before, okay, if we look at this diagram, we can see that the steel has a stiff, perfectly elastic behavior before we reach a level of strain of epsilon YD. Then it yields, and when we have yielding of the cross-section, we have that the material is capable to undergo high deformations, up to 10 per thousand, so 1%. Okay? It means that basically if we see a beam that is going to fail, if we have a ductile failure, we see that the beam is deformating, and is deformating even more. If the deformation is too high, it's too big, we have all the time, all the people have the time to get out of the structure before it fails. Otherwise, the brittle failure is the one that possibly occurs when we have all the structure that is, all the cross-section that is associated with a high level of axial force. Okay? Why? Because this, if we have a great part of the structure under compression, and this is typically for columns, not for beams, and the resisting reinforcement bars are not sufficient, we have that the failure can be associated to a strain domain that is not associated with a yielding of the reinforcement bars. If this happens, what we get is we have a brittle failure, so a sudden failure that is associated with very small deformation of the structure. That is something that we do not want, even if the structure is safe. But when we reach that failure, the kind of failure that we meet is, let's say, a bad one. So if you do not have any other questions, we can move to the last topic of the course, that is the behavior of reinforced concrete under shear. Okay, guys, please remember the 3 assumptions for the reinforced concrete. This is a suggestion for the exam. Okay, let's consider the shear strength of reinforced concrete beams. Well, this is something basically different from what we have seen so far, because so far we have dealt with computation of at each cross section. Okay, we were dealing with properties of the cross section. We said that in that peculiar cross section we had a value of axial force, bending moment, and so on, and we assumed that the cross section rotates remaining plane. We make a lot of assumptions focusing on what happens at each cross section of the structure. Regarding the shear for the reinforced concrete elements, it is different. It is different also from what you've seen in for the Italians in Scienze delle Costruzioni course. That is, this is structural design. It should be structural mechanics for the non-Italian students. Where you have seen how to compute the shear stresses, basically using the formula of Jurafsky that is directly associated with the value of the shear force acting at that cross section. But the behavior of reinforced concrete, and so design beams, does not focus on the cross sections, but on the entire beam. So now I'm going to explain it better. Let's consider a very easy case. So a simple supported beam with just one span of length L that is undergoing 2 loads applied at roughly 1/3 of the span in points C and D. If we perform the analysis of the structure, we can easily find that well, the reactions in A and in B will be equal to P, for that's trivial. So the shear force will be constant in the lateral parts of the structure of the beam, and whereas the bending moment will be constant in the central part of the structure. So the central part of the structure is subjected only to bending moment, pure bending moment, whereas in the lateral part of the structure we have pure shear force and linearly increasing bending moment. Now, from what you have seen so far, we need to put some reinforcement. And let's start with the longitudinal reinforcement. Here, since we have just one span, we know that bending moment will be positive, so we have tensile strain and tensile stresses in the bottom fibers of the cross-section, and we will need to put some reinforcement bars which run along the length of the beam and the bottom part in order to absorb the stresses that concrete cannot undergo. In fact, as we increase the loads, we expect some level of the form of crack patterns, so some cracking at the bottom part of the structure, and the path of these cracks is quite peculiar, and it is something like that. Now, if we compare these basically, we can discriminate two different behavior of the cracks. So we have one region, the central region, where the cracks are purely vertical, and it is better highlighted here. This is the first part where you will see cracking of the material. So if we assume that we are increasing progressively the loads applied to the structure here and here, at the beginning we will see some cracking at the bottom part of the structure in the central part of the span. And these cracks, as I said before, we expect them to be vertical. But as we increase the loads, we will see some cracking also on the lateral parts of the span. And these cracks will not be vertical, but will be diagonal. Why? Basically, we have seen that crack here is vertical. Why is it vertical? Because it is always orthogonal to the direction of the tensile force. Okay, let's focus on the central part of the structure, and it is better highlight also here. Let's consider a generic cross-section in the central part of the structure. We can draw the strain diagrams, and so we know that from Bernoulli-Navier assumption that what was vertical before will deformate, and it will rotate. This deformation comprises both compression strains at the top of the structure and both tensile strains at the bottom. We can plot continuous solid lines here that indicate something that is very simple to understand: the same level of compression of different fibers in different parts of the structure. So, if we compute the strain plot here, this strain level will be constant from here to all the points that are indicated by this line. And in this particular cross-section, we had that the neutral axis ranges until here, so we expect that there might be some cracks that reaches this height. Okay? Now, the direction of the tensile strains and of the tensile stresses obviously is orthogonal to the face of the structure. Is orthogonal and is horizontal. In reality, they are horizontal because they are going in, they are orthogonal to the direction of the tensile stress. So we have that basically, just to sum up the idea is that cracks are always orthogonal to the tensile forces. But in the lateral region, we have that this behavior is no longer horizontal, and so we have some inclination of all these lines. And this inclination of all these lines is orthogonal to the direction of all the shear cracks that will appear on the beam. Okay? So basically what we get is that we will find some portions of the structure that is associated with, that exhibits diagonal cracking. So this suggested, in particular to Morsch, it was a professor at Stuttgart University, and investigated this behavior in of the reinforced concrete elements under pure shear force. That the behavior, let's see it here, of the beam can be basically composes of different elements that interact with each other. Here we have this magnification, this cracking, that is diagonal with angle theta, that divides some struts of reinforced concrete from each other. So we have this all diagonal strut, puntoni in Italian, that still work. Okay, they are still capable to resist to any actions, but there is no possibility to resist in all the dimensions, in all the sections that are characterized by these cracking surfaces, because basically the material is no more homogeneous and it is no more capable to induce some resisting actions. So we can see that there is a part, a superior part, una briglia superiore in Italian, a chord that is purely under compression. So this chord is associated to pure concrete. Okay? Whereas there is also an inferior, a bottom chord, una briglia inferiore, that is undergoing tensile force. This chord is just associated with the reinforcement, the longitudinal reinforcement of the bar. That was not put there for the shear behavior, but for the bending behavior. But still allows the cross-section, the structure, to balance these failures mechanism. So the modelization, the modeling of this behavior is highlighted in the top dimension, in the top diagram, where we have this chord under compression, this bottom chord under tension, and then we have these diagonal struts, questi puntoni diagonali, that are associated with the safe parts of concrete. But in order to ensure the equilibrium of the structure, that can be seen as a lattice structure, una struttura reticolare, we need some other elements. These other elements will be ties, saranno tiranti. Strut and tie means some part that behaves under compression and some part that behaves under tension, under tensile stress. So, in your opinion, what are these elements, these diagonal elements? Obviously, these are diagonal or vertical elements in steel, because only steel can undergo tensile stresses. So, we will need, in order to ensure equilibrium, some vertical or some somehow inclined elements, metallic elements, in order to ensure equilibrium to the structure. These elements can be or inclined reinforcement shear bars if they have an inclination, so if they are diagonal. And typically in Italian they are called ferri-piegati. There was a technique that was used quite several years ago, but can be still used. It is more expensive. Otherwise, we use stirrups, in Italian le staffe. that are just vertical elements that are put, and here are exemplified. And they are put in the transversal direction of the beam, not in the longitudinal one. So, if everything so far is clear, and we are at a good point of this topic, let's see how this lattice structure can be associated to our reinforced concrete beam. Well, basically, we have considered a generic beam with a generic distributed load. We don't care about it. If we consider an equivalent lattice structure that is equivalent to our reinforced concrete beam, we can see that we have an upper chord that is working under compression, and the resistant force at this level, at this cross section, let's say, is NC, and there will be also some resultant tensile stress, tensile force at the bottom tie. The distance is obviously usually called Z, that is typically 0.9 times the distance between the top of the cross section and the reinforcement bars. But the most important thing is that Z is the effective length, let's say, okay, of this structure, and it is basically the lever arm. So the higher Z is, and the more bending moment it can, the structure can undergo. But here we have this diagram. In fact, we can solve the analysis of this structure. In this case, the structure is very simple because it is just a simply supported beam. If you're not familiar with this indication, it means that we are cutting the beam at the midspan, and the two parts of the beam are symmetric. So this is the meaning of this symbol for those who are not acquainted with this. And so, in fact, we can see that there is the change of direction of the diagonal part, because everything has to be symmetric. Now, well, the first thing we need to do is compute the bending moment. Computing the bending moment of a simply supported beam under a continuous load is something very trivial, and we can plot it with basically a continuous line in this diagram and also in this other one. No, better, in this line we do not plot the bending moment, but we plot the ratio between bending moment and the effective length. Okay, this is constant on the entire cross section, and so we'll provide us the value of the resultant compression force and the resultant tensile force for equilibrium equation. But we know from solving the lattice structure that the axial force does not increases progressively in this way, in a continuous way, but we will have some piecewise increase in correspondence of each node of the lattice structure. So when here we have, so far we have no upper chord, okay? So this part is not working for shear, let's say, but it will start from this part. So here we have an increase of the axial force until this level, and then it is constant until we have a new node. And so, in correspondence of each new node, we find the diagram of the upper chord, of the compression in the upper chord. Same for the bottom chord. Here we have the reinforcement that is already working right here, because we have a node, and this node exchanges some horizontal force with this part. So we focus on this line, we find this value of ratio between bending moment and effective length. This is the level of the tensile force that has to be provided by the reinforcement bars in the first part of the structure, and then again it progressively increases. Now, basically here we have again the same thing, but now the difference between this diagram and the next one is, okay, here we have a different load, but we don't care about it. We can have the load we want. The only thing is that the bending moment in this case will not be parabolic, not be quadratic. It was here, but it will be linear, obviously, because if we have 2Q of load, each reaction will be Q, and so the bending moment in the line, in the beam, will be Q times the axis, the coordinate of the beam. So this holds as before. And what changes is that here we are expliciting a value of the inclination of the struts, and we have a generic value of the inclination of the ties. So basically, the struts here have an inclination. Usually we use 45 degrees because, let me come back here. It is the average value of the inclination of the cracks when we have shear. Whereas alpha is something that deeply depends on the design, because it's something that I decide. I want to put some stirrups there, so in my structure, so I know that alpha will be 90%, 90 degrees. So it will be vertical, or better, it will be transversal to the beam. So in this diagram, the stirrup will be vertical, exactly as in this case. Otherwise, I can decide to put some inclined reinforcement shear bars, and in this case, I will have some alpha. This distance, the distance between each node, is equal to Z times 1 plus cotangent of alpha. If alpha is equal to 90 degrees, this equation is very easy. And this gives us also the spacing of this diagram. I think, okay, this is the very last slide. The next one is basically the same. So far we have dealt on how to compute the forces in the upper chord and in the lower chord. Okay, knowing what? Knowing only the bending moment. But we are interested in what happens in this strut and in this tie, because we will find some values of resisting axial force in this strut and in this tie that only depends on the design, so on how big the structure is and on the quality of the material, obviously. But here we have much less freedom to design. And then we will have to compare these quantities with the shear force that is associated to the ties and the strut. But in reality, it is very trivial, because this is provided by the resistant shear force provided by the tie and the resistant shear force provided by the strut in concrete are provided by these two equations that are simply derived from geometry. It is very straightforward to get to these equations, but it is quite tedious, so I don't want to go into details. Just notice that here we have 0.9d, which is, as I said before, this is what I was calling that so the effective length, and D is the distance between, let's come back, yeah. In this slide, it is called H. D is depth from the top fibers and the level of the reinforcement. But this is a formula, an equation that is also provided in Italian code, in the European code, so all the letters are well explained. So we have a first part that depends on the vertical dimension of the structure. Then we have the ratio, in this case. So we have something dealing with the dimension of the tie and the dimension of the strut. Regarding the tie, we have the ratio between the amount of steel in the web, so ASW, that basically is how many bars I am putting of reinforcement for shear in the cross section. This is over S. S means the spacing. I don't know why I make it with delta. Ah no, okay. S is the spacing between each different bar of reinforcement. So typically, if we have some stirrups, we have some stirrups at, I don't know, 15 centimeters. Okay, so that ratio will provide me this dimension. Whereas for what concerns the concrete, we have the only dimension is the depth of the beam. Then here we have the yielding design stress for the steel, and here we have the compression stress for the concrete. And then we have this stuff that may scare us, but it is something trivial. I mean, if alpha is 45 degrees, or if it is 90 degrees, these numbers are very simple to compute, and they just vanish. So basically, we have to, now we know how to compute this stuff. We only, when we want to design some shear strength on the reinforcement concrete beams, we know that the behavior will not be, let's say, ruled by what happens at each cross section, but it is something that involves the entire beam, the entire structure. Using equilibrium equation in the Morse strut and tie model, we end up with a value of shear force, of resisting shear force that is provided by the concrete, and the value of resistant shear force provided by the steel. We take the minimum of the two, so they will be different. We take the minimum of the two, and that value will be the resisting value for shear force of the real beam. And we compare the shear force that we compute solving the structure with that value. If it is, if this one is higher, then the structure is safe. Otherwise, we have to change something in the design. Maybe put some more stirrups, maybe reduce the spacing between them, or whatever. Okay. I've gone a little long on this part, so it is 12:20. I think, yes, this is the last slide of this course. So before wishing you good luck with the exam and good work for everything else, I know that this is not the only exam you're going to do. If you have any question about this lecture, this is a good moment. I hope that there are no questions. Because otherwise you cannot hear me and you just not heard anything.
Dear Professor, just for confirmation, we have to email Professor Gentile about uh, our
Whether you
desire to give the exam in presence or via internet or things like that. Am I right?
yes, that's correct. And please put me in copy.
Okay. Thank you.
So if there is no other question about this lecture, we can have. Okay, I would just go through the questions about other questions about the topic of the course or of the exam or whatever you want. Otherwise, I wish you good luck with everything and wish that you are safe during these times. That's it. Thanks for attending this course and for the brave ones that are here in the room, and for those who did it almost all the year. My best wishes to you all, and see you at the exam. Otherwise, if you have any question, I will be here in the room for some minutes to answer them.
I have a question. What type of questions do you ask on the exam?
Generic questions about the theoretical content of the course. Everything that has been shown by me or by Professor Gentile, you can be asked to explain it. I mean, I'm talking about generic questions. What can you tell me about the buckling of structures? So you know, you have attended some lectures about the buckling in the structure, so you will try to talk about generically of the buckling, and then I can ask you, okay, but there is some diagram. I'm showing you this diagram. Can you explain me the meaning of this diagram? I don't want you to be an expert of everything, but everything that has been explained, you should show that you got something. So if there is something in the slides that you see them and you say, "Oh, I don't know," maybe it is the time to ask me or about it. But this is not the time. You should have done during the course.
Thank you.
You can have both general questions or specific ones, or it also depends on how the exam is going. But this is true for any course you have ever attended. I mean, if the exam is not going well, I will not ask you something very detailed about something.
And do we start with the list of names?
For the marks.
Dell'appello?
Yep.
Iniziamo con l'appello.
No. I just go through me. Typically, it will be the professor, but
Alphabetically, like in order.
I think from top to. And the exam obviously will be long. I don't know how many of you were enrolled for that exam, but. And please, I remind you, as Mohammed Amin asked now, to write an email. I will receive hundreds of emails. Whether you want to attend the course, the exam in presence or not. I have no idea. But I think you should, if you go online, I'm the only one who does not know anything here. Because the professor is professor of the course. You know, because you're students.
Sorry, I have another question.
Yeah, please.
If I understood well, you were going to send us this file that it showed at the beginning of the class, right? With with the different results?
During the exam?
No, I was asking before the exam, were you going to share this PDF with the results of the exercises?
The slides.
Excuse me?
I don't know. I don't get what you expect me to deliver you.
All right, I'm sorry. So at the beginning of this class, Professor Gentile was commenting on the results of the exercises.
But for the written part of the exam?
No, it's just the results from the exercises that we delivered during the
Ah,
semester.
right. Okay, yeah.
Sorry.
No, sorry. Just that I cannot hear properly.
Oh.
The exam typically starts with a review of your homework. So you start with, okay, your degree was this one, your mark associated to the homework is this one. But if you can say, why did I perform so badly in something, if this is, and then you can ask about it, but typically this is not the case. Maybe it can happen that if you did something you performed something very poorly, or I can ask you about it.
All right.
But it's not mandatory. It depends.
All right. Thank you.
But obviously, if you have done something in the homeworks, we expect you to have done it yourself. So you should be able to explain. Maybe I can ask you, why did you divide this value times this other value? But that is trivial because you did it.
Yeah, of course. No, I was more asking, since you mentioned that we have a mark assigned that we were able to accept or not.
Okay. No.
So I was more focused into that. I was wondering how does that work?
Yes. Okay. I hope I have explained it.
All right.
I think not.
Credo che sapessi si mandate il file con le votazioni.
No. We will discuss during the oral exam, but you're not receiving the corrected version of the file.
All right, thanks.
Sure. Grazie.
Io non dico che chiedesse quello. Se mandate gli esercizi corretti fuori.
No. Cioè non manderemo le correzioni. Grazie.
Sorry, but we can accept evaluation before the exam. So just write to know marks, and after that.
If you performed well during the exam, you get just the mark proposed, and you can accept or have an oral exam.
Okay, during the exam, not before.
No. It depends on you. If you want to raise the mark, because maybe we propose you 22, 24, you want more, you can ask for some questions.
But if you do the exam, not the
Okay, it's clear.
Yeah. Direi che la possiamo battezzare. Okay, guys, if we have no more questions.
So, sorry, just one more question.
Yeah, go on.
I'm in the say in the white in the list I'm white.
Okay.
For me, it's the same in the exam if it's in presence or at distance. So I don't know what you prefer. Maybe, as I understood, maybe online.
Yeah, I think that Professor Gentile, from the recording.